in some ways, you guys put me a little bit in between a rock and a hard place. A lot of the problems on the test were rather involved. I think I had said that I would not accept just answers. I needed to see work. And there was a good number of people in the class who did not send me work. The grade needs to get from the MyLabs gradebook into that column in Blackboard, and I put them in that column in Blackboard when I check your work. And so if there is no work, I cannot justify giving you full credit. I know there are apps out there where you can just take a picture of the problem and get the answer. There were some people, when I looked at their work, they had magically the right answer, but all of their work was wrong. I need to see work that supports your answer, or you're not getting credit. Second, I apologize because I'm going to do a little bit of scolding, and I know the scolding doesn't apply to all of you. I'm sorry for those of you who got the test in on time on Sunday, but I was really disappointed with the volume of emails that I received saying, oh my gosh, I thought I had till midnight. I questioned myself, so I double checked, and I saw in the notes, both Monday and Wednesday at the beginning, I specifically said noon Sunday. I used the word noon, so everybody, I meant 12 o'clock noon, not 12 o'clock midnight. It specifically said noon. And I looked at the settings in Blackboard, and the test was available from midnight after midnight Wednesday morning until noon on Sunday. All of my coworkers think I'm crazy for giving any class more than one day in which to do a test. Most of them give one day. Most of them actually just give 1 hour class time. And so I was truly disappointed with the number of people who sent me panicked emails that they hadn't taken the test yet and it was afternoon. It's that's uncalled for. You had Wednesday, Thursday, Friday, Saturday, and half a Sunday. You had 4.5 days in which to do that test. Shame on you for leaving it for the very last minute and leaving it until after it was due. Beyond that, though, I'm truly concerned with all of the papers that I got where there was no work. If there's no work, there's nothing for me to grade. There's nothing for me to put in that Blackboard grade book. So I think that at the beginning of the semester, when I talked about showing work, I said that if there was a problem that was worth 10 points and all the work was right, but just the final answer was wrong, you would probably get 9 out of 10 points. The answer is only worth 1 point. And so flip side, if all I have is an answer and no work, you'll only get 1 out of 10 points. So if you're one of those people who did not give me any work, you need to either come to me during my office hour tomorrow and talk to me after class today, or send me an email and see what we can do. But again, even in not necessarily just this class, but in some of my other classes, I could very easily tell that there were people who got the question wrong, and then afterwards, looking at the right answers, recreated their work. And so I'm real leery of taking work submission after the test. So I'm at a loss. So from now on, you will only have 1 day in which to do a test. The times will be very clearly spelled out. And if there is no work, I will not grade it. You will not get a grade. Everybody clear on that?
Yeah.
Yeah. All right. If so, we're switching gears a little bit. Up until this point, we were looking at manipulating algebraic expressions, simplifying expressions, simplifying fractions, simplifying radicals, working with exponents. It was chapter P, preliminary chapter. because it dealt with, some of the background knowledge that you need. We're going to start looking at solving equations in this next section. But before we start solving equation in this next section, there is information in section 1.1, which is due on Wednesday, on the Cartesian plane. And so, just wondering, has anybody heard of that terminology, the Cartesian plane? And before I go too much further, can everybody hear me okay? The others, my 10 o'clock class, there's some people who said it wasn't clear. So I'm using the microphone instead of talking into the computer. Can you guys hear me okay?
You're good. Yeah.
Yeah, I can hear you.
Thank you. Anybody hear of the Cartesian plane?
No.
Sorry, no.
I bet if I draw it, you'll all nod and smile. The Cartesian plane is actually the fancy pants name, fancy pants being the technical term, right? For the coordinate plane. Does that look familiar?
Yeah.
Yes.
And it's called the Cartesian plane because, just a teeny tiny bit of math history, it's named after Rene Descartes. And if any of you have ever taken a philosophy class, you might have heard of Descartes in philosophy. Rene Descartes was a groundbreaking philosopher and mathematician. And if you ever get a chance to take a math history course, you'll find that there's a great overlap between philosophy and math. And a lot of what was done in math was actually done more as a exercise in reasoning. And a lot of what was done in math was done long before there were practical applications, just kind of thinking skills. There's a big relationship between math and philosophy, especially with things like logic. So anyways, it's named after Rene Descartes. But as I draw this, does everybody remember your axes? You have the x-axis and the y-axis, and their number lines. They're number lines that are perpendicular. And they intersect at a common zero. The horizontal is the x-axis. The vertical is the y-axis. And so they're number lines intersecting at a common zero. Because they're number lines, they should be, like any number line, evenly spaced and some semblance of scale put on them. You don't necessarily have to label every number, but you need to label some. If you're drawing by hand, it's important that you label which is the X and which is the Y, because in a way it tells you to, which is the up of your paper, which is the down of your paper, which is sideways. Can anybody remember what those axes are used for? They're used to locate points, which are given as ordered pairs. And so does everybody remember seeing a point as an ordered pair, X, Y? They're in alphabetical order. The X value is also sometimes called the abscissa. And the Y value is also sometimes called the ordinate. Back in ancient times, we were held accountable for those words. And so in terms of the ordered pair X, Y, they're in alphabetical order. X comes before Y. And so if I think of those words abscissa in ordinate in alphabetical order, the X value is the abscissa, the Y value is the ordinate, putting both words in alphabetical order. So if I ask you to locate in the plane point A, which has as its coordinates 3, 2, that tells me that the X value is 3. So I'll look at 3 on the X-axis and picture a dotted line that goes to the 3 on the X-axis perpendicular to the X-axis. That would be all of the points that have a abscissa of 3. Then I do the same with 2 on the Y-axis. And I find that they meet here. And so this would be my point A, 3, 2. How is everybody at plotting points?
Good.
Good.
Just so you know, Lonnie and Maddie can't get in. They said they've tried the password and everything over and over, and it's still not letting them in.
Okay, do you guys mind? Do you guys think I should take a minute and send them a separate email with it again? Or
Yeah.
should, yeah? Okay, give me just 1 minute. Email, and go here. Oh, the word 1 was from the one. Control C, send email, select users. Who am I sending this to, folks? Or should I just send it to everybody in the interest of time? You're going to get it all again.
Yeah, that's fine.
Okay, I just sent it to them again. All right, so now back on track. Over here, if I called this point B, what are the coordinates of B?
Be -1, -2.
Thank you. And is everybody comfortable with that? I think in that very first homework in my labs, that introductory homework, there was some problems using the graphing tool. Hopefully everybody comfortable with that. One more point that I'd like to look at right here. Is in the chat. Can anybody remember the fancy pants name of this point here that I'm scribbling on? It's getting bigger and bigger and bigger as I scribble.
Is it origin?
Yeah, the origin is the point 0, 0, and it's where the axes intersect. Now, can I turn the page, folks? I'm going to.
Go ahead.
The axes divide the plane into actually 5 regions. I'm going to do a real rough sketch here. Has everybody heard of the 4 quadrants? And the quadrants are usually numbered with Roman numerals. The first quadrant is up here in the upper right-hand corner. Everybody likes that one best because it's where everything's positive. And we'll see that from there, we're going to go around in a counterclockwise direction. And you're going to find when we start talking about trigonometry that we go in that counterclockwise direction because we think of angles opening upward. And so this will be quadrant 2, this will be quadrant 3, this will be quadrant 4. So I've got my 4 quadrants. What would that 5th region be? The 5th region is going to be right on your axes. So that if I'm right on one of the axes, I'm not going to be considered in a quadrant. So I have the 4 quadrants plus their boundaries, your x-axis and your y-axis. So far, so good. If so, I'm going to scooch up and we're going to switch gears for just a little bit. And we're going to look at an equation in 2 variables. And we're going to see that the solutions are ordered pairs whose coordinates satisfy the equation. And so in that first homework for section 1.1, you're going to see a question or two that asks something like, is 1, -1 a solution of the equation 3y plus 2x equals 1. And so I'm guessing you've all seen how to answer a question like this, how to do a check. What should I substitute in for x if I'm using that point 1, -1?
1.
1, beautiful. And what should I substitute in for y?
-1.
And we're going to just substitute to check. And so we get 3 times -1 plus 2 times 1. Does that equal 1? Does -3 plus 2 equal 1? And so here the answer would be no. Instead, what if I ask, is 5 -3 a solution? This time x is 5, y is -3. And so I'm checking just 3 times y plus 2 times x equal 1. That's -9 plus 10, or 1 equals 1, and it checks. Is everybody all right with that?
Yeah.
Is -1 a solution? Here, 3 times y is 1, plus 2 times x is -1. Well, that's 3 minus 2, or 1 equals 1, and so it also checks.
I'm sorry, but how are you getting a 3 and a 2? I'm like, might
But
be a
it's
little
using
confused.
that equation up at the top, the original
Oh,
equation.
okay.
Y
I just want to double check.
equals 1. I'm recycling. And do you notice that if I have two variables, an equation can have more than one solution? And it's possible an equation in two variables can have an infinite number of solutions. How do you spell infinite? Oh my heavens. I-N-F-I-N-I-T-E, thank you. Number of solutions. It would be all the ordered pairs that satisfy it. So is everybody familiar with the idea that if we have more than one variable, it's very common to have many, many solutions, more than one solution? And it gets us to the idea then of what's considered the graph of an equation. Which is the set of all the points whose coordinates satisfy the equation. And so sometimes we're asked to sketch the graph of an equation. And to start with, we're going to make tables of values. And so, is everybody all right if I turn the page?
Yep.
So let's sketch the graph. Of the equation. And this time, let's look at something like y equals 9 minus x squared. And again, I'm going to do this by making a table of values. You can make your table of values as you see fit. I always learn to make a column for x at the beginning, a column for y at the end, and I write in the middle the equation, y equals 9 minus x squared. I think that in this first section, you're going to be given values to use for x. So let's look at values from 3 down to -3. And then we're going to substitute those in. And so when x is 3, y is 9 minus 3 squared. When I take 9 minus 3 squared, what do you get?
0.
Beautiful. When x is 2, I get y equals 9 minus 2 squared, which would be 5. When x is 1, I get 9 minus 1 squared, which would be 8. When x is 0, I get 9 minus 0 squared, which would be 9. Now, be careful when you substitute those negatives, especially if you're using a calculator to evaluate it. When I substitute a negative number, I like to remember to put parentheses around it. 9 minus negative 1 squared would be 9 minus 1 or 8. Next, 9 minus the quantity negative 2 squared would be 9 minus 4 or 5. When x is negative 3, that would be 9 minus the quantity negative 3 squared, or 9 minus 9, which is 0. And then when I go to sketch it, labeling my x and y axis, what I didn't say before, and I should have, I apologize, is when you draw your axes, you want to put arrowheads on them because technically they're infinite in each direction. Try the best that you can to evenly space. So we've got the point 3, 0, 2, 5, 1, 8, 0, 9, negative 1, 8, negative 2, 5, negative 3, 0. And then we'll connect the points with a smooth curve. And folks, this is where I have to apologize. I'm a mathematician and not an artist, so my graphs always don't look as pretty as they should. Is that one, though, all right for everybody? Can anybody from a past life remember the name for a curve of that shape?
Parabola.
Parabola, great. And we'll look a little bit more at that idea later. When we talk about graphing, we talk about intercepts of a graph. And the intercepts are where the graph crosses the axes. We can have an x-intercept, and we can have a y-intercept. And actually I said a x-intercept and a y-intercept. We can actually sometimes have more than one. If I look at that graph that we just drew, does everybody see this has two x-intercepts? Here the x-intercepts are 3, 0, and negative 3, 0. And does everybody notice that they both have a y value of 0? And so the x-intercept will always be the point of the form a0, because in order to be on the x-axis, the y value must be 0. And to find, we can substitute y equals 0. Again, looking at the graph, over here, my y-intercept is a point. The x value is 0, the y value is 9. And does it make sense that everywhere on my y-axis, I would have an x-coordinate of 0? So the y-intercept will always be a point of the form 0b. And to find the y-intercept, we'll substitute 0 for x. So far, so good.
So the A and the B are just describing the
They're variables for the A would be the x coordinate of the point. So here, A would be negative 3 and A would be 3. B would be the y value of the point. So in this example, B would be 9. And if you notice for the y-intercept, it occurred where we substituted in 0 for x, and the x-intercept would be the x value we would have gotten if we substituted in 0 for y. All right? I'm going to try a couple more graphs, and then we're going to go on and we're going to try to start solving equations. Can I move this up and look at a couple more graphs?
Yeah.
Okay, next graph. Let's sketch y equals, the absolute value of x minus 1. And for this, let's use x values from the set -2, -1, 0, 1, and 2. So again, at this stage of the game, in order to make these sketches, we're going to make the table of values, substitute nx to get y. This time our equation is y equals the absolute value of x minus 1. And for x, we'll plug in the numbers -2, -1, 0, 1, and 2. Doing the first together, we get y equals the absolute value of -2 minus 1. What's the absolute value of -2?
2.
2. And 2 minus 1 is 1. I'm going to shut up for a minute and ask you folks to please complete that table. Does everybody have their corresponding y values done yet? Or do you want me to wait a minute? Hearing nothing, I'm going to carry on. When x is -1, y would be 0. When x is 0, y would be -1. When x is 1, y is 0. When x is 2, y is 1. So my points are -2, 1, -1, 0, 0, -1, 1, 0, 2, 1. And this time, when I connect the dots, what I get are two straight lines that intersect at that point 0, -1. You notice that it has a very distinct V shape. And you'll find that usually equations that involve, a lot of times, equations that involve absolute value, if there are no exponents, will have that distinct V shape. As I look at that, what would you tell me the x-intercepts are? And again, going on the picture, I see it crosses the x-axis twice. And what we said before is if I'm looking for where it crosses the x-axis, I have y values of 0. And so does everybody see my x-intercepts would be -1, 0, and 1, 0.
Do you always read that left to right?
You know, in terms of like listing the points, order doesn't matter as long as you have those 2 points, -1, 0, and 1, 0. It would be fine if you put them in as 1, 0, -1, 0. Does that answer your question?
Yes, thank you.
And then for the y-intercept, we had said that the y-intercept is on the y-axis, so the x value will be 0. And so what's the y value of that point? -1.
-1.
Make sure, I do believe that in my labs, when they ask for intercepts, they ask for them as ordered pairs. Make sure you put in both. All right? One more. This is an interesting example. What if did I turn that too fast or is everybody okay?
You're good.
What if I ask you to sketch y equals 1 over x? And this time, let's have x come from the set -2, -1, -1/2, -1/4, 0, 1/4, 1/2, 1, and 2. Table of values. We're plugging in x values to find y. We're using y equals 1 over x. And we're substituting in -2, -1. Oops, -1/2, -1/4, 0, 1/4, 1/2, 1, and 2. Does everybody have their table set up? Can I start substituting values?
Not just yet.
Okay, let me know.
Okay, you're good.
Okay, so when x is -2, y is 1 over -2, which would be -1/2. When x is -1, y is 1 over -1, which would be -1. Now, when x is -1/2, I have 1 over -1/2. Does everybody remember that 1 over means I'm taking the reciprocal? And the reciprocal of -1/2 is -2. Here, the reciprocal of -1/4, 1 over -1/4, would be -4. What happens when I plug in 0? What's 1 over 0?
0.
Check it with does anybody have a
1.
calculator? Check it with your calculator. Can anybody with a calculator please put in 1 divided by 0 and tell me what you get? Is anybody getting the word error? Remember, we can't have a 0 in the denominator. So this is undefined. Then when I go to +1/4, the reciprocal of +1/4 is 4. When I have +1/2, the reciprocal of +1/2 is 2. 1 over 1 is 1. And lastly, 1 over 2 is 1/2. And so when I look at this graph, x, y, x values go from 2 to -2, and somewhere in there I want to mark 1/2 and 1/4, positive and negative. The y values go from 4 to -4. So let's see, at -2 I have 1/2. At -1 I have, oh, I'm sorry. Yell at me, folks. At -2 I have -1/2. At -2 I have -1/2. At -1 I have -1. At -1/2 I have -2. At -1/4 I have -4. Then at 1/4 I have 4. At 1/2 I have 2. At 1 I have 1. At 2 I have 1/2. There is no value, it's undefined when x is 0. And so I get a curve that looks like this in the third quadrant. and then a curve that looks like this. It's in the first quadrant. And we'll see that the x values can get close at 0, but never equal 0. And so as you look at this graph, do you see that there are no x-intercepts and also no y-intercepts? And so not every graph has an x-intercept, not every graph has a y-intercept. Some have neither. Has anybody seen that graph before? 1 over x.
Yes, I have.
Good. Well, you see that it will become a recurring theme more so when you get into pre-calculus and calculus. I do believe that you're going to look at that graph a little bit more also in Math 111. Now, sometimes you're asked to find intercepts without making a graph. If I ask you to find the x and y intercepts of the equation, of the graph, pardon me, of the equation, and I'm going to have 2x minus 3y equals 6. If you're a glutton for punishment, you'll make a table of values and sketch it. But it's easier to remember that in order to find the x-intercept, we're going to just substitute y equals 0. And so my equation is 2x minus 3y equals 6. Becomes 2x minus 3 times 0 equals 6. Since 3 times 0 is 0, that just becomes 2x equals 6. And so x is 3. And so my x-intercept would be the point 3, 0. And likewise, for the y-intercept, we have to remember that if I'm on the y-axis, my x value is 0. So I'll substitute in x equals 0. So in my 2x minus 3y equals 6, I get 2 times 0 minus 3y equals 6. Since 2 times 0 is 0, that just becomes negative 3y equals 6. And so dividing, I get y equals negative 2. And so my y-intercept has an x value of 0 and a y value of negative 2. So far, so good. And so if I remember correctly, most of that section 1.1 deals with graphing, which would be like what we've just done. Any questions?
Nope.
No, great. Then going on to section 1.2. Section 1.2 deals with solving equations. And we're going to start by solving linear equations. In one variable. And when I talk about a linear equation, in one variable, linear equations are going to be first degree equations. Oh dear, that word degree is a blast from the past. I was surprised as I was looking at people's tests over the weekend. There was a question that involved, I believe it was the subtraction of two polynomials, and then it asked for the degree of the solution. And I was surprised to see that some folks didn't quite get that one. Do you remember that the degree is the highest exponent? And so when I look at a first degree of equation, the highest exponent on the variable is 1. We're looking at polynomial equations, so we're not going to necessarily deal with fractional exponents or negative exponents. And so if I look for the general form of a linear equation, I'm going to have ax plus b equals c, where a, b, and c are real numbers. And to solve them, we want to get an equivalent equation of the form x equals d, where d is a real number. And so does everybody remember, if I'm trying to solve an equation, what I'm trying to do is get that variable alone. And you know, we did a little bit of solving equations when we were trying to determine the domain of a rational function, when we were trying to find the values that made that denominator equal to 0. In 1.1, the author makes a point of talking about what it means to have an equivalent equation. And to get an equivalent equation, I need to use my properties of equality. And we're going to have 4 properties of equality. The first is the addition property of equality. And the additional property of equality says that if A equals B, then A plus C equals B plus C. Or if you want it in more wordy matter, inequality remains the same if you add the same quantity to both sides of the equation. The subtraction property says that if A equals B, then A minus C equals B minus C. Or I can subtract the same quantity from both sides of an equality, and it remains equal. There's the multiplication property. Of equality that says if A equals B, then A times C equals B times C. Or I can multiply both sides of an equation by the same value, and it remains equal. Usually here, though, we specify that we don't want to multiply both sides by 0. So we'll say we want to multiply both sides by the same non-zero quantity. And then there's the division property of equality that would say that if A equals B, if I have an equation, then A divided by C equals B divided by C, or I can divide both sides of the equation by the same value. But again, here it's really important. Remember, we said you can't divide by 0. You can't put a 0 in the denominator of a fraction. And so we're going to divide by a non-zero quantity. And hopefully everybody is familiar with the idea that in general what these properties say is what you do to one side of an equation, you've got to do the exact same thing to the other side. Can I turn the page and not lose anybody? Or do I need to wait a minute? Not hearing anybody, I'm going to turn the page. And so to solve a first degree equation, to solve a linear equation, the first thing that we're going to want to do is simplify each side as much as possible. like to say that that word simplify means we're making it simpler. So if you can always remember to simplify each side independently before you try to solve an equation, it's going to make your life simpler. Then we're going to use the addition or subtraction property to get all the variables on one side. Then, after we get all of the variables on one side, we'll again use the addition, subtraction property, or subtraction property to get all the constant terms on the other side. So once we've got all of the variables, all the letters on one side, all the constants, all the plain old numbers on the other side, then what we'll do is we'll use multiplication or division property to get a coefficient of 1. On the variable, and then we'll have that equivalent form x equals, or whatever our variable is, equals. And then it's always important that you check by substituting into the original equation. We always want to go back to the very original equation before we did any work. The equation as it was given to us when we checked, because we're checking to make sure we didn't make any mistakes along the way. And so I've got a few examples here that I'd like to go through and do. Can I scroll up? Is everybody caught up?
Go ahead.
Okay, thanks. So first example, let's look at 6x minus 3 equals 63. If we were in the classroom, I would be doing this on a document camera and not on a touch screen. And what you would see me do right now is put my big old fat thumb over the 63, and I'd be looking at just the 6x minus 3, and I'd say to you, can I simplify 6x minus 3? Are there any like terms there? And I believe the answer is no. Then I'd put my thumb over the 6x minus 3 and look at the 63 and say, can I simplify that? And again, the answer is no, because there's only one number there. Then I'd look at it and I'd say, okay, let's look at both sides. The variable is only on one side, so I don't have to worry about that. Now, because we're trying to get the variable alone, we'll move that constant term. The opposite of minus 3 is plus 3. If I add it to one side, I have to add it to the other. So that gives me 6x equals 66, at which point I want to stop and say that when I do, I think it's important to put the equal signs in between to make sure that all of your equal signs add up. Because sometimes I see people who start strong, but they lose their equal sign, and they end up doing the same thing more than once on one side of the equation. If you line up your equal signs, you'll always make sure that you're working on both sides. Now, in order to get a leading coefficient of 1, I'll divide both sides by 6, and I get x equals 11. How's everybody with that one?
Good.
So then when we do the check is 6x minus 3 equals 63. Going back to the original, I'll put in 11 for x. And then I'll work, let's see, that's 66 minus 3, or 63 equals 63, and it checks. In an ideal world, we'd have time to do all of the checks together in class. But because I'm worried about time, can I, for the rest of the examples, leave the check to you guys? Next example, I have 5x minus in parentheses 2x minus 10, close parentheses, equals 35. With this one, can I simplify on the left-hand side? Does everybody remember if I have a minus sign in front of parentheses, I want to think of there being a little -1 there. So that'll give me 5x minus 2x. And when I distribute that -1, it becomes plus 10. And then combining like terms, I get 3x plus 10 equals 35. Now to get the variable alone, it's only on one side. So I need to move the plus 10. The opposite of plus 10 is minus 10, giving me 3x equals 25. And then to get a leading coefficient of 1, when I divide by 3, I get x equals 25 thirds. Don't be afraid if your answers are fractions. You'll see the phraseology: express your answer as an integer or the ratio of integers. When they say ratio of integers, again, a ratio is a fraction. So write your answer as a fraction in simplified form. Sometimes they will not accept a decimal. If it says a ratio of integers, they want a fraction. That one all right? If so, next example is a little bit different. What if I have 3x plus 5 equals 2x minus 13? And with this one, I can't simplify either side, but there's a variable on both sides. I want to get the variables together. Would you rather move the 3x or the 2x?
The 3x?
Okay, if I move the 3x, I'm going to have to subtract 3x from both sides. Gives me 5 equals -x minus 13. Now to get the x alone, I'd have to add the 13 to both sides, giving me 18 equals -x. X is not quite all alone. I'm going to divide both sides by -1, and I get x is equal to 18. That one all right. Next example. Let's say I have 5x plus 9. Say it again. Question? You okay? Let's say I have 5x plus 9 equals 9 times parentheses.
Chloe, shut the fuck up.
Who's talking? Everybody all right?
I'm good.
Okay. So what would you do first with this one?
Factor in the 9.
Okay, so that gives us 5x plus 9 equals, what is that? 9x plus 9 minus 4x. Then what would you do?
Combine the like terms on the right side.
So that gives me 5x plus 9 equals 5x plus 9. Then we want to get all the variables together. So I'm going to subtract 5x from both sides. And I get 9 equals 9. Does anybody notice anything about that? Is there a variable left? No. So let's look at that 9 equals 9. Is that true or is that false?
True.
It's true.
It's true, and it's always true. And when you go through, if you get an equation that's always true, an equation that's always true is called an identity. It'll be true no matter what value you plug in, so that the solution set is all real numbers. And so when you're solving your equation, if the variable disappears when you're doing everything right and you just have a number equaling itself, that's always true. It's an identity. That equation will always be true, and the solution will be all real numbers. Next example. Let's look at 3 times in parentheses x plus 2 is equal to 7 plus 3x. Does anybody want to tell me what you would do in order to solve this equation?
Distribute the 3 on the left side.
Beautiful. So that gives me 3x plus 6 equals 7 plus 3x. Now again, we always want to try to get the variables all together on one side first. So does everybody see the need here to subtract the 3x from both sides?
You get 6 equals 7.
Does 6 equal 7?
No.
No. And so do you see how this is always false? And so if when you do the addition and subtraction property to get your variables together, if you eliminate the variable and you get a false statement, you get, ooh, what happened there? You get what's called an inconsistent equation. Can you guys hear me?
Yeah.
Yeah.
An inconsistent equation has no solutions. So the solution set is empty. You can show the empty set by the braces with nothing in it, or you can show the empty set with that symbol for the null set, the 0 with the slash through it. That one all right.
Yep.
So if the variables disappear and you get a true statement, we've got an identity, an equation that's always true. And if the variables disappear and you get a false statement, we get an inconsistent equation, which means we have absolutely no solution. Next, let's look at equations with rational coefficients. Oh, Lord. My hand keeps hitting that toolbar at the bottom. Sorry about that, folks. So let's look at an example like 4/3 x plus 1 equals 9. And this equation, I have a rational coefficient or a coefficient that's a fraction. I'm going to start the same way. I can't simplify either side. The variables are only on one side. And so I'm going to try to move the constants together by subtracting 1 from each. And that gives me 4/3 x equals 8. Now, if I have a rational coefficient, rather than dividing both sides by the fraction, it's easier to multiply both sides by the reciprocal of the coefficient. So I'm going to rewrite that equation. 4/3 x equals 8. And the reciprocal of 4/3, we're flipping it, I get 3/4. And whatever I multiply one side by, I'll multiply the other side by. Over here, 3/4 times 4/3 would give me 12/12, or 1x. And then on the other side, how you multiply that, I guess, depends on how you learned your arithmetic. If I multiply straight across, that gives me 24/4, which is 6. Some of you might have learned instead to cross cancel factors when you multiply. It'll also give you that 6. And so if you have a rational coefficient, if you have a coefficient that's a fraction, usually it's easier to multiply both sides by the reciprocal than it is to divide by that fractional coefficient. Next example, let's say I have x over 5 minus 1/2 equals x over 6. And this equation is full of fractions. Most people find it a little disconcerting if their equation is full of fractions. And so there's one step that you can legally do to get rid of the fractions. And so what we'll do is we'll clear the fractions by multiplying both sides of the equation by the, oh Lord, I just looked at my watch and I'm trying to write fast and so my hand is misfiring, by the least common denominator of the fractions. And so, between 5, 2, and 6, what's the least common denominator? What's the smallest number that you can divide evenly by all three?
1.
Not that goes into them, that they go into.
I would say 2, but 2 doesn't really go into 5.
No,
60,
how about, I'm thinking we can go a little bit smaller than 60. How about 30? Can 30 be divided by 5? Can 30 be divided by 2? Can
Yeah.
30? Yeah. And so what we're going to do is we're going to take each side of that equation and multiply by 30. In doing so, does everybody see the need to distribute on the left? And then on the right, we'll just put the 30 over 1. And if I choose that right denominator, 5 goes into 30 6 times, 2 goes into 30 15 times, and on the other side, 6 goes into 35 times. And you see how I have no fractions left. And now I'm going to solve that equivalent equation. And so let's see, I've got 6x minus 15 equals 5x. Let's subtract the 6x from both sides, giving me negative 15 equals negative x. And so dividing by negative 1, we'd end up with x equals 15. And so if you have an equation that has all sorts of fractions in it, your best bet is to find that common denominator of the fractions and multiply each side by that common denominator. And I'm making a note to myself that that was the last example that we did. That was where we stopped. Anybody have any questions on that one?
No, but I'm here. I was late. I couldn't get into the Zoom at first. Just want to make sure you mark me for attendance.
Okay, all right. Let me stop recording.